Hello everyone. We're looking at how to determine if two figures are congruent today. We've talked in the past about congruence as it relates to segments and angles. How do you know if angles are congruent? How do you know if segments are congruent? But if you combine segments and angles together, you can create figures like triangles or quadrilaterals or other polygons. And now we want to know how to determine if the entire triangle is congruent to another triangle, or if the entire polygon is congruent to another polygon. So use this as an illustration here. Imagine for a moment you see at the factory site this car roll off the production line, and then a minute later another car rolls right off the production line. Now if they're made at the same plant and they're made at the same production line, they should be the same car, right? But how do you really know? You'd have to check all of their matching parts. You'd have to check this tire and match it with that tire and analyze if they're the same. You check this grill with that grill. You check the mirror with the mirror. And you go on and you check each part. You open up the hood and then there's all those parts in the engines, right? So there's thousands of parts and you'd have to check every part with every matching part on the next car that came out of that production line. And if all of those parts are exactly the same, then you could say the car as a whole is identical to this second car. You could say the cars are congruent, right? We're doing that essentially with polygons. We're saying, how do we know if this triangle is identical to this triangle? I mean, it certainly looks like it, and we're not proving things yet. This is just a demonstration, but if we took a piece of tracing paper and labeled the vertices with the triangle ABC, and we translated it, that means we're shifting it over, in this case to the right, and line it up, do we see that the left sides match? Do we see that the bases match? Do we see the slanted sides match? But even more than that, if we take a look at the size of the angle, do we see that the size of the angle A is in fact the size of angle G? And they do appear to match in that way. So you have to match all the parts. So that's what we're looking at here in steps 1 and 2. We just quickly used tracing paper to demonstrate that copying so you could compare those matching parts. And what do we notice as a whole about the triangle? Well, it appears the triangles are the same shape and size. And we've seen this idea before when we were in our second unit talking about transformations. We translated, we reflected, we rotated objects on the coordinate grid, and we realized they were examples of rigid motion, that they maintained the same shape and size. So we're going to use rigid motion today to explain these concepts of analyzing not just the figures as a whole, but the individual parts that make up a figure. So here we just did a simple example of a translation. So if we look at the parts of the triangle, we have observed that it has 3 sides, but also 3 angles. And with the example of the car, we had to compare thousands of parts to make sure that they were the same. Then we could determine the cars were identical. Here, that means we have to compare 6 parts. We have to make sure that all 3 sides of the first triangle are congruent to all 3 sides of the second triangle. And the same for the angles. Make sure all 3 angles of the first triangle are congruent to all 3 angles of the second triangle. And when we do that, we are creating congruent corresponding parts. So complete the following congruency statements by listing the congruent corresponding parts. And these are the parts that match, in other words. So you can see that angle A was identical in size to angle G. So that's the first pair of corresponding and congruent parts. So angle A is congruent with angle G. Angle B is my second angle, so let's give that a double arc. That will pair up with angle E. And again, they're not only corresponding, but they are also congruent. So there's 2 features we're looking at. Angle C and angle O pair up, and they were congruent as well. And then we have to check all the sides, and we already checked the height, and that was the same length as the height on the second triangle, so that means segment AB is congruent with segment GE. And then the base of the triangle, give that a double tick mark, and the base of the second triangle. So segment BC is congruent with segment EO. And the final side then, of course, give that a triple tick mark. So segment CA is congruent with segment OG. Now, because we've analyzed all 6 parts and we've seen that the 6 parts on the first triangle are identical to the 6 parts of the second triangle, then we can say because the individual parts are congruent, then that means the figure as a whole, the triangle as a whole, is going to be congruent to the other triangle. And what we want to do is we want to communicate how those triangles compare to each other, and we do that with a congruence statement. So the following is one possible congruent statement. So this is triangle ABC, which is the first triangle. We're starting at vertex A and going counterclockwise around. So triangle ABC. Now if A is what I listed first, then on the next triangle I have to start at the matching part, at the corresponding part of angle G, and again go counterclockwise around. So this would be triangle GEO, in the same way we call this triangle ABC. And that's what you see right here. Triangle ABC is congruent with triangle GEO. So the order of the parts match. So notice that if angle A is congruent with angle G, and I list A first, then G must also be listed first in the name of that second triangle. If angle B is congruent with angle E, and I list angle B second, then in this other triangle I need to list E as the second letter. And then same with C and O. They are a corresponding and congruent pair, so if I list C as the third letter in the sequence, then that means the matching letter of O must also be the third in the sequence. Okay? Now, as you may know, we can name this triangle in a variety of ways. Instead of going counterclockwise around, we could have gone clockwise around. We could call this triangle ACB. And if I did that, triangle ACB, now I've changed the order of the letters, and that means when I name the second triangle, I must also change the order of that letter so that they match. Because remember, if A is listed first, then G must be listed first in the other triangle. Here, if C is listed second, then O is listed second. And if B is listed third, then E is listed third. So the order of the letters matters, because you can look at the congruent statement and easily see which pairs of parts are your matching parts. Let's say we started at vertex B and went counterclockwise around, so triangle BCA. So triangle BCA is congruent to triangle. Alright, well B is the first letter now. That pairs up with E, so E is the first letter. C is the second letter, that pairs up with O. And A is the third letter, that pairs up with G. Instead of calling it triangle BCA, what if we had gone clockwise around and called it triangle BAC? So triangle BAC is now congruent with triangle EGO. And lastly, what if we had started at vertex C and gone counterclockwise around? So triangle CAB. In the same way, C pairs up with O, so O has to start. A pairs up with G. And then lastly, B pairs up with E. So triangle CAB is congruent with triangle OGE. And the last possibility is, what if we had gone clockwise around and called it triangle CBA? And that's congruent with triangle OEG. So the takeaway here is that the order matters. Alright, so the order matters, and we want to make sure that we match up those corresponding parts. So just as a word of caution here, sometimes you'll notice that we use slightly different phrasing to distinguish between these two pairings, even though this is a congruent symbol and this is a congruent symbol, but here we're listing matching parts, and here we're listing not just matching parts but identical congruent figures as a whole. So on the homework you're going to notice a difference between these. So these we are not calling congruency statements. They're actually going to be described as congruent corresponding parts. Okay, and when it says to write a congruence statement, that is going to name the entire figure. So the congruence statement names the figure as a whole. So if it's a triangle, we're naming the triangle. If it's a polygon, we're naming the polygon. Here we're naming segments, here we're naming angles, but it's not the whole figure of the triangle itself. So we just call these congruent corresponding parts, meaning these parts are sides, these parts are angles, and these are not parts, these are the figure as a whole. So the congruence statement is the statement that shows the entire figure is congruent to the other figure. Alright, so we looked at a brief example for translations. Now we're going to look at a couple other variations on this using some of the other transformations we've seen in the past. So if you take a look at example 2 on the next page, we're going to work with not a triangle now, but we'll work with a rectangle, and we're going to reflect it. And if you remember, if you reflect an object, it should stay the same shape and size. We would expect this to be congruent to the original. And we're just going to work that out and see that play out. Now because we've got 4 sides, I'm going to use a variety of different colors to keep organized when we reflect this figure, so we can kind of easily see in the diagram where those corresponding parts are to be found. Alright, so here are the 4 parts. I've already plotted them A, B, C, and D, so take a moment and plot them on your own graph paper, and I'll connect the sides in just a moment, but that's what the other colors are going to be. We're going to reflect it over the y-axis, so we're going to see that this shape will flip over from the left side to the right side. So what I want to do is start by coloring in some of the sides with different colors. So let's say from A to B, I'm using my red color. Let's say from B to C, I've got my blue. Let's say from C to D, I've got my green color. And then on the last side from D to A, I'll use the black color. If you have a highlighter, you could highlight different colors on different sides, or if you just have one color, that's okay, we'll still make it work. But this is hopefully able to be seen a little more easily as we pair up those matching sides. So we're going to reflect it over the y-axis. You may remember we did that just by counting the distance from a point to that y-axis. So if point C is 1 unit on the left side, then 1 unit on the right side, we called C prime using prime notation. But in this case, instead of using prime notation, they're just renaming it. Alright, so here I used point C, we reflected it, so this is now point T. I'll put a T right next to that. D, again, 1 unit to the left, so 1 unit to the right lands here, and D is paired up with H. Let's call that point H. Point B is 1, 2, 3, 4, 5 units on the left side of the y-axis, so 1, 2, 3, 4, 5 on the right. B is paired up with O. And then lastly, A, again, is 1, 2, 3, 4, 5 on the left, so 1, 2, 3, 4, 5 on the right. A is paired up with M. Now because this segment that went from A to B, I colored in red, if A is reflected to M and B is reflected to O, then the segment that connects A to B is going to be paired up with this segment from M to O. So I'm just matching the colors. So those are your corresponding parts. The top segment that went from B to C, B reflected to O and C reflected to T. So the top side here is reflected over here to the top side from O to T. The right-hand side of the original figure from C to D, C reflected to T and D reflected to H, so this entire side connecting C and D reflects to this side connecting T and H. So that's my third color in green, and then lastly the bottom side I've got in black. So we've labeled all of those corresponding parts, and now we want to list all the corresponding sides and corresponding angles. Now, remember, they may look to be congruent, and we kind of know they already are, but that's not the point. The point is you first have to check all the corresponding parts. You have to check all the corresponding sides and all the corresponding angles, and only then do you actually know if the figure as a whole is congruent. Alright, that's the method. So let's list all the pairs corresponding sides. Alright, so I have this side AB in my first color, red. Segment AB is congruent with segment MO. On the top side, segment BC, that is congruent with, now notice B pairs up with O, so as I name this, I'm going to name it segment OT. Again, technically when naming segments you can name the letters in either order, but I'm just matching up the corresponding parts. So B pairs up with O, and C pairs up with T. On the third side we have segment CD, and so that's congruent with segment TH. And then lastly, segment DA is congruent with segment HM. But that's only half of it, because we have to now check all of the sides. All the angles in addition to all the sides. And I'll just do this in one color here. So we have angle A is congruent with, and that reflected over here to M, so angle M. Angle B is congruent with angle O. We have angle C congruent with angle T, and D with H. So angle D is congruent with angle H. Now, we would actually have to verify that they are congruent, and we can do that by counting the length, right? So we could say segment AB is 1, 2, 3, 4 units in length, and segment MO is 1, 2, 3, 4 units in length. So yeah, they are congruent. And same, we can count the top, we can count the side lengths of the green lengths, and then we can count the bottom sides. And yeah, so each of those will be congruent. And then when we're checking the angles, we can see we have right angles that pair up with right angles for each of these. So yes, we know all the angles are congruent. And so now we can actually see that the two rectangles are going to be congruent. Now there's lots of possible ways to write congruent statements for the rectangles. We could call it rectangle ABCD or ADCB, or we could start here, call it BCDA or BADC. Right? Just pick a vertex and either go clockwise or counterclockwise around it. There's lots of possibilities, and here we're just identifying two of them just for a little bit of variety. So let's start with ABCD. How about that? So figure ABCD is congruent with, and remember the order of the letters matters. So A is paired up with M. So A is in front, so M has to be in front. B is second, and that's paired up with O, so O is second. C is third, that's paired up with T. And then D is last, that's paired up with H. So that's one possibility. Let's do something different. Let's pick C as a starting point and go in a counterclockwise direction. So let's call it CBAD, for example. So figure CBAD is congruent with, so C pairs up with T, B pairs up with O, A pairs up with M, and D pairs up with H. Alright, so those are just two examples of how we could name congruent statements for the rectangles. Alright, and in our final example we're doing something quite similar, but this time with a rotation. So this time we're going to take a rhombus and we're going to rotate it. So here are the 4 points that we're plotting, so I've already got that here, just started. There's point D, E, F, and G. I'll connect the sides in a moment using my different colors. And then we'll rotate using this rule, and that's just a reminder for what that rule was when rotating 180 degrees. All right. So from D to E, I'll use in my first color of red. From E to F, I'll use my second color of blue. From F to G, I'll put that in green. And lastly, from G to D, I'll put that in black. So again, that will help see with the rotation where the parts are going. So in order to apply the rule for a 180-degree rotation, we're going to negate the x and negate the y. So we're calling point D in its new place, not D prime, we're just renaming it with a new letter, so let's call that K. And I'll put this new rotated information right here. So K will be coming from point D, and we're just changing the signs on both. So we have 0, -4. Point E is paired up with P, so P comes from point E, so 3, 8 is now -3, -8. F is paired up with R, so point R will be -6, -4, and then point G is paired up with Z, and Z is -3, 0. Let's take a moment and plot those points. So K is at 0, -4, so down 1, 2, 3, 4. Point P is at -3, -8. Point R is at -6, -4. And Z is at -3, 0, so left 3. Let me say something about point E. I realize that sometimes my students in my class will freak out when a point is like off the edge of the grid that's provided. Remember, the coordinate axis is a plane, and a plane goes on forever in each direction. So we know that the x-axis doesn't literally stop here, it goes on forever, and that's what the arrow is for. And same with the y-axis, it goes on forever, that's what the arrow is for. So don't be concerned if a point falls off the provided grid. Usually we try to keep it within 1 or 2, and you just plot where you think that extra grid line would go and call it good. Alright, so we used the first color, red, from D to E. So from D to E, I used red, so I want to use red from K to P. Alright, so here's K to P. So that way you can see those are the corresponding sides. The second color in blue I used from E to F. So E to F is paired up with P to R. So P to R is going to be in my blue color. And then my third color in green, I use that from F to G. So F to G pairs up with R to Z. So R to Z. And then there's only one side left, so of course that would be the fourth and final color, the black. So when you do the rotation, it's a little bit easier to see now that this first side in red rotates all the way over here. That's the corresponding part. In the same way that angle E is formed by the red line and the blue line, that rotates all the way down to the bottom, and again it's formed by the red line and the blue line. So those are your corresponding angles, those are your corresponding sides. So again, we did learn in the past that when you do a rotation, the figures remain the same shape and size. So yes, we do know they are congruent, but we're learning this new technique, this new method where in order to determine if figures are congruent, you really have to first make sure that you match up those corresponding sides and angles. So we're going to list them out here. So that first side from D to E, segment DE, is congruent with segment KP. Alright, second color is blue. Segment EF is congruent with segment PR. Third color in green, segment FG is congruent with, let's see, segment RZ. And then lastly, segment GD is congruent with segment ZK. And then all of the angles, right? So again, I'll just list the angles in one color. So angle E rotated down here to angle P. So angle E, excuse me, let me double check that. Is that right? Yeah, so E down with P, angle P. F rotated to R, so angle F rotates to R, G rotates to Z, and the last one is D rotates to K. Now here we're listing them as congruent. We didn't actually count the distances or find the angle sizes, so that's why the tracing paper is suggested to use here in this particular example to verify that those corresponding sides are in fact congruent and that those corresponding angles are in fact congruent. So let's just take one of these angles. Let's take angle E and let's rotate this about the axis 180 degrees, and let's see if angle E really is the same size as angle P, and yeah, it is. My sketch is a little bit sloppy here as I didn't use a ruler to draw it, but we do have congruent figures. Alright, so again, let's write two congruent statements for the rhombus. So if I use the original rhombus, DEFG, figure DEFG is congruent with figure KPRZ. And let's change it up for some variety. Let's start with G and go counterclockwise. So if we call this figure GFED, that would be congruent with, alright, so G is paired up with Z, so Z has to come first. F is listed second, F is paired up with R, so R comes second. The third letter is E, E is paired up with P, and the last letter of D is paired up with K. So notice also that when we are naming figures, that with naming triangles, we put the little triangle symbol in front of the three letters, but if we're naming another kind of polygon, like a rectangle or rhombus, there's no special symbol for those. There will be a special symbol for parallelograms, but we'll learn about that in a future unit. So here's the big idea. These transformations do not change the size and shape. The transformations are type of rigid motions. And again, our book sometimes uses the word isometry to describe a rigid motion. And this is the big one right here. For two figures to be congruent, what must happen? All of their corresponding parts must be congruent. Now let me just give one final example here, and let me put down an example of a figure that illustrates what we mean by corresponding and corresponding parts congruent, because that's what we've seen up here in these diagrams. We've had corresponding parts and they were congruent, but what if they were corresponding but not congruent? So as an example, here we have rectangle ABCD, and if I were to make some sort of transformation where it ended up being a really small rectangle, right, so I'll call that A prime, B prime, C prime, D prime, for example. You still have your right angles in there, okay? So if you look at those corresponding parts, you can see that angle A does correspond with angle A prime, and they are congruent. But if you look at just a pair of sides, look at segment AB, it does correspond with segment A prime, B prime, but they're not congruent. So these two figures are not congruent. They do have corresponding parts, but every pair of corresponding parts must be congruent for the figures to be congruent. So these figures are not congruent. So notice the difference between what we mean by corresponding parts versus congruent corresponding parts. And that's it for today.